Well, hello and good evening, good afternoon to everybody. Welcome back to the build that we're doing. My name is Charlie, call sign November Juliet 7 Victor. And with us leading the show is Rex, Harper, W1REX, and Steven, N1SH. We are doing the Tuna Tin 240th anniversary Buildathon. And so welcome everybody back. This is the third episode or the third stream that we have done. If you've missed the other two, you can catch them on Rex Harper's YouTube channel, which is just do a search for QRP Me, or you can do it on my channel, Red Summit RF. And so first episode, we just kind of went over the schematic and talked about a little bit of stuff to get prepped. Second episode, we were all about building and had that iron out and we could smell bacon, man. It was great. And so here we are, we're wrapping things up, and I'm just going to go ahead and turn the time over to Rex right away, and we can get started.
Okay. All right. Thank you very much. Welcome back to the third and final session on the Tuna Tin 2 build. Hopefully, everybody's got their kit built by now. I mean, there was a couple people who bought them late, so they're still in transit, but I think 99.99% of everybody's got a kit in time to do a build before today. So now the question was, the program for today was to help get people who don't have a working kit finished, problems, debug problems or troubleshoot whatever. And then we're going to go into using the tools, the dummy load and the RF probe to measure stuff on the kit, make sure you're working okay. And then we're going to go talk about the potential of increasing power or moving into other bands. But the first thing I was warned about was not warned about, but reminded that we had talked about building the key that was part of the kit. Now, I included a document in the web page about building the key. But if you didn't catch it and you don't have a key built, then we can do a very quick run through on that. Meanwhile, while I'm doing the key business, maybe people can be commenting in about questions or problems that they have with their kit, is whether or not they finished it or what they've got for issues, so that we can address them.
And the first one we have is
we got one.
William. His 10 microhenry inductors appear to be blue green, or not blue green. They're beige. Is that okay?
That's okay.
Yeah.
Well, yeah. Does it say black? I mean, brown, black, and then gold, silver?
Yeah.
Okay. That's just a different family. If you notice, they're probably much bigger than the other ones. They're much tubbier, and that's because they were bigger for more current through them. And indeed, those are probably legacy inductors I have for the Rockmite kit, because I kit them with those big ones. The ones that people got were the same family, but a different manufacturer, Borns, and they were green based.
Yeah.
And they're about that same size, but they again, different manufacturing and different style.
Yeah.
So yes, those are fine.
He says it doesn't look like it's gold silver. It kind of looks like it's gold.
Okay. Better gold is better tolerance.
Better tolerance.
Those are probably gold silver. I think is probably a 10%. And I think gold is probably 5%.
So he got the golden ticket.
He got the golden ticket.
Willy Wonka's going to be looking for him.
Those will work more gooder in that circuit. But yeah, they will work just fine. Yep. Okay. Any other ones that are of note?
Well, start with the key, right. And I'll feed them to you as we get them.
So these are the parts for the free key. And you've got a base, and then you've got a key that a lever that sits on top. You got a connector, you got a jack for and a header. So the first thing you should do is, and I did put a document on the website for this. So the first thing you do is take a piece of wood. Here's an ordinary piece of wood, but I have a laser, so I made it a little bit on the fancy side. So there's my straight key base that I made, and you could just make it out of a piece of pine, or in the case, a piece of this is 1/4-inch plywood, although this is a little bit more difficult to deal with because we'll show you. But the first thing you do is you put the key on your base, and then with a very sharp pencil or a let's say a pilot style pen or something, mark the holes, the 2 holes for the screws, and then the holes for these little components. Because when you solder them up, hang on a second. When you solder them up, there's going to be solder dimples there. So this thing's not going to lay flat unless you've got either a hole there or you pound a little hole. So what I did is the first one I built, I put on a piece of pine, got the holes all knocked out, and then I took a nail and I just pounded the nail into all 1, 2, 3, 4, 5, 11 holes. And that gives it room for the solder joints to stick down inside.
Nope, you're good.
We're good? Okay. So once you find your piece of wood and you put it on there like that, and you mark your little holes, and again for the components and the 2 screws, then you can start building your kit. And this is a stereo jack with internal switching. So there's 2 extra pins on this. And so you have to cut them off. So let me go get my good pliers, and the pins you want are on the outside. Those are the actual contacts, and the inner ones are the circuits that are made when the jack is not when the plug is not put in. So we cut those 2 off.
So William also said he measured the resistance of the input power. Is there a value that should be? He said it was about 30 megohms for him. Is that the resistance across the input? Across the power connector?
Well, there's going to be a diode there, so it's going to be almost infinite. Especially if you got the leads wrong.
Yeah.
You're going to be trying to read across the back resistance of a diode.
Yeah.
Other way around, let's say you go through the diode, and there's an awful lot of circuitry there. I would have.
Maybe we'll come back to that when we're looking at the schematic.
Yeah, well, either that or we can actually measure it on one that works. Okay, so I'm going to very quickly build this thing because we don't want to spend a lot of time. So this is going to be the fastest build you'll ever see. It actually.
Well, there's not a lot of components.
There's just 2 components you solder.
You're soldering on the stereo jack.
So I'm going to start this. Now I just soldered 1 pin because it's at an angle here, so I'm just going to put it on something, and I'm going to reheat that while I make the board flat.
Yeah.
Okay. Now I can go ahead and hit the other 2 pins. Yeah. Okay. I see it now.
You want me to grab my drill while you're doing that?
Or a hammer and a nail? No, I don't need a drill.
Okay.
Okay, because I'm not going to use your thing.
Oh, okay.
Okay.
No, you're not going to use my piece of wood.
I'm not going to use your piece of wood. I'm going to use my nice fancy. So then the next thing is the little 6-pin header. So we can plop that on. Okay. I'm going to hold it with my finger. Okay.
The shorter ends go into the board, right?
Huh?
The shorter ends go in the board, right?
Shorter end goes in the board. Yep.
Yes, that's the solder side. Okay. So I'm holding it on, if you can see, I can hold it with my fingernail, and I'm holding on one end, and I'm going to solder the other end, and I'm going to use my.
Otherwise, you'll heat your finger up nice.
That's right. And I'm going to use my new patented Cobra technique. I made a little thing. I'll show it in a minute, but I made a 3rd hand for holding the solder. And all I got to do is solder 1 pin. Okay. And now I can take a look at it, and I know it's flush, it's straight and everything. I like everything. So I can put it back down on the thing. I can forget about my Cobra and come over here and do the other 6 pins. Other 5 pins, excuse me. Okay. See, it's all built, sort of. In my case, I made my super deluxe. Ordinarily, these would be on a piece of wood, and these would be holes that or dimples that you put in with a nail. Okay. I can just go ahead and slap that down. And when I find those points, you see I've got holes or dimples. I've got drill holes or burn holes.
Just so it sits flat on there.
So it sits nice and flat. Okay.
And if you don't have the holes in there, it just won't sit flat.
It'll
but
be
still
all
work.
crookedy. It'll still work, but it'll be all crookedy. So in this case, now there's 4 washers, 3 of which are big and 1 is small. And the fact that the washer is not small is the fact that it's half as tall as these washers. It's a skinny washer, thin. I had to pay extra money for that. So when you stack them up, you can put 3 down. No, I'm going to do it the other way around. I'm going to take my longer screw and I'll go through the board, making sure I got the label up. Then I can stack 3 of these on it.
So you can just adjust your action.
Right. And this one, I'll show you when I get this thing on. I need a screwdriver. Get it and they'll get started. And I can screw that down. I'm going to move this out of the way like that. And you could, if you don't like the I'll show you in a second. I'll put this together. It actually works pretty good with just a stack of 3. And it all depends on the head of this screw here. This is the pan head, very short screw. And it works just fine with that 3 stack on the other side. Come on. Okay, I can slide that back like that.
So
Okay.
slide it out of the way first and show it on the close
Oh.
camera.
Okay, so there is everything. Now
So
watch.
the three big ones go on the back, and then there's one that goes on the front.
No, I don't put anything on the front. See,
Okay.
I still have this washer on the.
Okay, got it.
Okay.
So
And-
show it side on to the close-up camera. So
Well, I'm going to try to do this. Let's see if I'm going to zero in right there. See that gap? Okay. All right. See the gap of the key? If I screw this, if I put that out, take this bolt out.
you can adjust it by taking that out.
I'm going to put the skinny one in there. And I'm going to raise the head of this contact bolt. And I'm going to make it much more sensitive because your lever doesn't have to travel very far now. Doesn't have to travel as far. Let's find that. Let's find the magical spot.
Yeah, the camera's over here.
Yeah. Well, I'm trying to look at the. I gotta get that finger out of the way. Is what I gotta do. Let's see.
Yep. So you've got.
See that gap? I'm trying to get it on the paper so you can see the gap with a white background. See the white background through there? Very, very fine gap. So you don't have to move that hardly a tad to make the contact. So again, it's just a little bit more sensitive with that. Now, of course, it's a circuit board. You can always bend it out just a little bit. And there's the gap right there for the contact.
Yeah.
That's it. So these two jumpers, let's say I wanted to use this on a rock mite. This is a straight key going to a rock mite. On a rock mite, you have to actually short one of the paddles to ground, and then it will recognize the key as a straight key instead of a paddle.
Yeah.
And it'll go into straight key mode. So in this case, I can take one of these pins and go to ground, and the other one go to contact. So this is the configuration of the key if I want to use that on a rock mite. I got one pin shorted. That's shorting one side of the cable, and the other pin has got the contact. So that will go fine into a rock mite, and it would actually work on a tuna tin also if you have both of the jumpers made on a tuna tin. So this key is configured to work with either rock mite or a tuna tin, just the way
And
it
is
is.
that the configuration folks are going to want it for?
For a tuna tin, doesn't matter.
Okay.
Either one or both, doesn't matter. Okay. Because we jumpered them together when we built the board. Remember, we put the jumper on the tip and the ring.
Yep.
So any set of paddles will work. A key will work. Anything will work on a tuna tin.
Yep.
But again, if you've got a rig that already has a keying chip inside,
Then
it
you
might
want-
get
yeah.
persnickety about what it sees.
Yeah.
It doesn't want to see both of them closed. It wants to see one closed and one variable.
Yeah.
Okay. So that's how we built this key. Now you just take a nice aux cable and plug it into the back and plug that into your key and your rig, Tuna Tin, you're ready to go. So we're going to use this thing now. Okay. Did we get any more people with problems troubleshooting?
I haven't seen any more come in.
Oh, come on. Everybody built it. That's good. Everybody built the
Yeah.
kit. They got no problems.
At least one person sounded like they already built it.
Well, I know a couple of
They
them.
said they made it. That means they either made the key or they made it to the stream here. So
Okay.
it could be one of the
Well, yeah, or they made the key or they made the kit. Who
Yeah.
knows? Okay.
And,
You've got to be a little bit more clear about
I
this.
think JT was asking, is crookedy equal to cattywampus?
Cattywampus
that's
works
the- yeah.
just for us, especially up in when you're up into Mattawamkeag
Yeah.
or Pasadumkeag. Cattywump
Yep.
is a very good term. I think that's in fact there's a town up north called Medibumps,
Yes.
and being Cattywump in Medibumps is probably a late Saturday night after
Yes,
drinking
yeah.
deal. Okay. Anything else? I don't have any. I don't have to solve anybody's problems.
Okay.
This is going to be a short night.
Yeah. Hadn't built a free key yet. Is it okay to use just a regular straight key with a mono mini plug?
Yeah, perfectly fine.
You could just have two wires hanging out. And touch
You
them
can,
together
yeah,
with
we
a paper
got.
clip
We
or
don't
something.
even. In fact.
There are many options for
Yeah,
you.
there are many options. Okay, I mean, for testing purposes, we don't really need much.
Yeah.
Two wires work just
You can
fine,
be tapping two
Or-
wires together.
or a wire in a alligator clip.
Okay, so I think we might be getting into some people with some problems. Let's see.
Problem. Oh, come on, we got a
Initially, there was
problem.
no power after the key. The trace from the key to jack to C2 looks broken. Oh, they made a temporary jump and now have power along the key line, but not getting any signal out.
Okay.
So the power after the key.
Oh, I got to look at a
Let me
board
Bring up the
or a schematic.
Let me bring up the board.
I'm going to bring up the schematic. Okay, so we got power after the key. Go down to the plus line.
Yeah.
Okay.
So, well, this comment's not going to come in
Okay.
really well, but so no power after the key. The trace from the key jack to C2 looked broken. So is that C2 right there below the key?
Yeah,
So
Hmm.
soldering
that's
that
interesting.
that should fix
Okay.
that problem.
All right,
You
so-
should see, what should you see along that? That's
Well,
not
this is 12 volts all the way across, all the way down to the inductor. So if you don't have any power along that line, I mean, if this is broken, you patched it, okay. But you should be able to measure 12 volts at the top of R2, 12 volts at the top of R4, and R6, and one side of L2.
Yep.
You should be able to just check all those and make sure you got plus 12, and you can check them all off. Then go to these two. See, this is just a voltage divider, and this is a
Yeah.
voltage divider. So you should be able to go to those two places and be able to measure the.
And those are on the schematic, right?
Yeah. You can see right here, it says 1.0 volts. You should be able to read. This is 47K and 4.7K. So that's 1 out of 11. So it's 111. So it's 0.9 volts roughly.
Yeah. So the numbers that on the schematic that are in red should be showing you. You should see.
No,
Whoops.
no, it's the.
No, I was saying here there should be 11.7 volts or somewhere
Correct.
around 12 volts.
That's in blue.
Yep.
Okay.
And
That's the
that what you were
non parentheses numbers are DC voltages. Okay.
so that 11.7 there, the 1.0 down here,
Yep,
11.6 here.
Okay. Now you won't.
Yeah.
Yeah. Okay. 11.6 is right. Okay.
Yeah.
So you should be able to read all those voltages.
Yeah.
Okay. At R2, R4, R6, and C8, you should be, or L2.
Yeah.
Once you read those, then double check and make sure that you've got the junction of R5 and R6, that voltage divider, and
Sorry,
what happened to my
something- yeah,
screen?
I don't know. Something-
Okay.
there we go.
and over at Q1, the junction of R1 and R2. Okay.
And then
All the way over. Yep.
Yep.
All the way up. No, R1 and R2, all the way over.
R1 and R2. All the way over which way? Yeah.
Right
that's
side of the sheet.
Yeah.
Right there.
Well, you were saying all the way over, and I was going to the other way. And I'm like, I don't know.
Well, we
Okay.
got a mirrored image here,
Yeah,
so I
yeah.
can't tell him which way to go because I don't know
You're
which way
right,
he's
right.
going.
Yeah.
Okay. So all those are DC voltages, and if you don't have one of those voltages, it's going to affect your circuit, your operation. Now, let me tell you probably the first thing you should do if it's non-operational is go to the back side of your board and just look at the quality. Just go right around there and look at the quality of your solder joints and make sure that you don't have a cold solder joint.
Yeah.
If you've got something that looks like a ball on top of the board,
Yeah.
then it probably doesn't have a good connection. And it's very often where, let me get my pointer here. Very often where you've got a ground. Let me have your bare board, would you?
So somebody else asked, is 13.8 volts okay?
Yeah, I mean that's all a function of your power supply.
Yeah.
Okay, and I do believe I think on there it's listed on the schematic as being measured DC voltages, key down plus minus 10. I think those were measured with right 12 to 14. So I think they're measured off of 12 volts.
Yeah.
See, it says right here 12 volts. So these all were based on 12 volts.
Yeah.
If you got
Yeah, that's-
13.6, then you got to read a little bit higher.
That's one of the questions I had. So I just wanted to mention Richie's Radio Room gave a donation of $3 again. So Zippy, we really appreciate that. We
Okay,
wanted to acknowledge
that's good. Okay, he'll buy someone a snack. I'm going to need one after this.
And Jan, I'm sorry, I don't want to interrupt, but Jan asked, see only RF 0.97 on collector Q1. All DC voltages are okay. Oscillators-
0.97 on the collector up here, where it's supposed to be 4.0. Okay, let's take one at a time. Let's just finish talking about cold solder joints. And a lot of times, if you look at the bare board,
Let me see if I can use the clip.
well, let's see. Let me see if I can zero in. Okay, and I got to. Okay,
There.
now I got again. I'm mirrored, so it's going to take me a little while to get there. Right there. See that point? That pad right there. All the little rays. That's going to ground. If you soldered on that thing, and your solder, if you don't wait long enough, if your solder iron is cold, not hot enough,
Mhm.
then you might have a ball of solder sitting on top of that, not really
Making a
connecting, not
connection,
making a good connection. That's a typical place that you will find an error on a board when it's not soldered well. Okay, and you think you soldered it, but you don't have a good ground, and that will affect lots of places. I'm just trying to see where one of these grounds on the voltage divider, if that's up in the air, then this can't work.
Yeah.
Okay, because there's no voltage divider to set that transistor where it wants to be. Same over here. If that thing is cold right there, then you've got a one resistor coming in and not the other to set the bias on the transistor. If you've got a cold solder joint right here, okay, then this path for operating that transistor is incomplete. So yeah, you got to check them all. I guess if you look on I should put a picture on my website of the board flipped over, so that you can recognize where to look. So if you have this thing, you can correspond to where to look for all the grounds, because when you cover them with solder, they're hard to see.
Yeah,
very hard to see.
Okay, so says he's seeing. I think he means I think he's writing 0.97 RF 0.97.
Where?
He's got 0.97. But on collector Q1, all RF 0.97 on collector Q1. All DC voltages are okay. Oscillator is working. he hears it on the radio, RF 1,14 volts on collector 1,14 volts. Check all part locations. Oh, on 114 on collector of Q2. That
Instead of
should
12.
That
Yeah.
should be 11.7.
11.7.
Yeah.
Yeah, DC. That's DC, not RF.
DC. Yeah, he said DC voltages are okay. So
yeah. Okay. Well, then what that's gonna fall into let's go with the RF probe and run that through.
Yeah.
Okay, later on. Is there anybody else who's got
I have a question.
Okay.
I'm trying to get mine powered up for the first time. The middle pin of the RCA jack, is that ground or is that positive? I don't want to reverse
the middle
the RCA jack.
Oh, you mean the center, the actual actual tip part? That should be positive.
The tip's positive and the shield around the
yes,
outer jacket is negative.
Yeah.
Okay, thanks.
Just like coax. RCA is a very cheap coax. It was good for video up to about 6 megahertz, if I remember correctly.
CMK said he didn't get a 56 PF cap. Can he use a 65 PF? He didn't get a 56. Can he use a
56 was up here. Okay. 56 is up here.
Yep.
That's going to affect the. Sure, it wasn't inside one of the one of the RCA jacks, because there was 3 or 4 people reported that one of those loose little capacitors was stuck in the RCA jack.
Yeah.
That 56 is a part of the harmonic low pass filter. It will affect it somewhat. Okay, so you might want to like tack it in, and then when you get a 56, and I'll send you a 56. Okay, when you tell me to, then you can put the 56 in. You'll get the full effect of the filter, but it will affect the output of this thing and how well it functions. Okay.
So it sounds like a couple of people are ready to power their boards up.
Okay, well then let's go to it. I will put this blank one away, and we'll get. This is one I built this morning. Okay, I'm gonna unplug our meter for a minute. Okay, I'm gonna get the schematic out of the way. So I've got a cheesy red RCA audio cable that I plug into my power.
And you've got that plugged into a 12-volt power supply.
And I've got that cable terminated with a pair of alligator clips that I can go to my power supply. So I have a 12-volt power supply, bench power supply over here. And I'll rig that up, and that's good. So you want to make sure that you turn your power supply on after you plug that in, because you can with that probe being 12 volts, you can actually do some nasties on it. But I mean, it's not serious, but it's just in the habit of connect your cables, then turn on power. Okay, that's just good practice. I'm going to put the key in. Good practice. Okay, this is not
the key over onto the white paper there.
Okay, I'll bring the key over. Okay, sorry, we got all these cables here. I can't seem to get them out of the way. Do that. That's better.
Why don't you use the power jack instead of the RCA connector?
Why don't I use the power jack? Okay. Okay, we talking.
Yeah, we talked about this last time. You've got that where the 12 volts is, that you could put in one of those screw terminals.
You could put in screw terminals, which cost a lot more money. Okay.
Yeah.
Which means I sell the kit for more money. Yeah. Okay. But when I made this 40th anniversary, I made it as true to the Tuna Tin as I could. The Tuna Tin had all RCA connectors.
Yeah.
Okay. They even, I do believe, they even had an RCA. I can't remember if they had an RCA for the key or not. Yeah. Can't remember that one.
Anyway,
go look at
the board has. You could put one of those.
It has a dual footprint, and you can put a dual screw terminal there. And some kits I've done that with a little more pricey. I tried to make this kit so it was as cheap as I could sell it.
Yep.
Okay, and still be worth. The other thing is, being a Tuna Tin fanatic, which I am for many, many years. I go to we call it a friend of mine we call it the Limerick Shopping Mall, which happens to be the transfer station or the dump.
Mhm.
And we have a place called the Take It Shop, and people who bring stuff, they leave it in the Take It Shop if it's good. And of course, we also have these like 5 or 6 big giant gaylords over there, and we have to pay to get rid of electronics these days. TVs, stereos, everything. And they go into these big gaylords, and they all get hauled off to the recycling place. Excuse me. But I have a good relationship with the people who run the shopping mall, and I get a chance to look in there and see any kind of good stuff, which typically means RCA cables hooked up to old TVs and VCRs. So I collect them.
Yeah.
And I have no problems making cables out of RCA plugs because I do a lot of Tuna Tin stuff.
Yeah.
But yeah, you could put a thing there. I just didn't put one in the kit.
Okay. So you've got your power connected, your keys connected.
Yeah. I want a dummy load in here. Okay. So here's the dummy load right there with the full 49.9 resistor. Okay.
No, we made that last Sunday, didn't we? Yeah, we made that last Sunday.
I think so.
Yep.
I can't remember exactly when. So I'll plug that into the antenna jack and make sure that my switch is on T for transmit. So now the output of this goes directly to the antenna, which has got a dummy load in it. Okay.
Okay.
What's the frequency?
Pardon?
The frequency input.
7.03.
7.03 or thereabouts. We found ours on 7.02.
No,
I think.
No, that's where we listened to it.
Oh, that's where we listened to it. Yep.
Because we were 7.0, 7.029.
029. Yep.
7029 is so I'm going to turn my unit on, my power supply. You can hear the radio in the background.
Oh, I'm just getting a constant signal.
Where are you now?
7028. Oh, isn't that where we were before?
No.
Oh, hang on. 7029. Oh, I hit the wrong button. Sorry. $7028. I had you there before.
Mm-hmm.
That's an upper sideband.
No. Where are you?
7028. Oh.
Go up higher.
7029. Oh, darn it. Hang on. 7029.
We're working on a rural band radio. We don't have a shortwave radio. I mean, an actual ham radio over there.
I'm on 7029 now.
Go to 7031.
7031.
We just had this, just a little while ago.
Power off for a minute. Yeah, that's definitely your signal on 7028. You get your key wired correctly?
I got it wired.
Well, good, because we're going to do troubleshooting.
No,
right?
there we did. I think that was it.
Yeah.
Okay. Because
So, show how you've got your key wired.
I now have both of them on contact.
Show it. Oh, let me put it on the right camera. Bring it right up to it.
Okay.
There you go.
Okay. See, both of them I have on contact because remember we wired the kit with tip and ground both shorted.
Yep.
Okay. And I had built this key and say if I wanted to run on a rock mite, I would have one shorted and one not. Okay. But on a Tuna Tin, since we did both of those, it was constantly on.
Yep.
Okay.
And
so with both of them off.
Whoops, I guess the radio's not on. Yeah, you can see it's just a.
Okay. Well, they can hear it.
Yeah.
Okay. Well, I just moved it. Damn it. Okay.
They can.
Get it off my bench. Okay.
7028.
Now I'm going to.
At least I hope you guys can hear that. I think it
Could
comes
you hear
through
that,
the
Charlie?
microphone.
Could you hear that?
Yeah,
Kate?
barely. Yeah.
All right. Okay. I'm going to turn my power off, take my dummy load out, and hook up this nice meter over here.
So we're going to hook up a watt meter to it.
I've
so
got a
that we
watt
can
meter
see
hooked
that.
up. I'm going to turn my power back on.
Hang on,
Okay.
Let me get this aimed at
I
the
got to
watt
fine
meter.
tune this.
Okay.
You ready?
I don't know yet. Yeah, it's a little crooked, but
Okay. Well.
there we go.
Okay. What scale are we on the watt meter?
Let me put it on the half watt.
Half watt.
So we're right on.
Right there.
Here,
We
right
got
there.
2.25,
Yep.
roughly 0.26. So we got
So
260
right down there.
milliwatts. Okay. Of raw
CW
RF
power.
CW power. Okay. So that's about what this kit was designed for. Okay. So I'm working, my work rig is just working just fine. So now that I know it's working, I'm going to hook up the RF probe. As soon as I find the RF probe, what do they do with the RF probe? Yeah, fell on the floor.
Yeah.
Okay. I've got a lot more cables I have to deal with my RF probe. Okay. So
You've got the RF probe.
okay, I'm
Up to our
all right, I'm gonna try to bring this meter on here and cram everything.
Yeah.
Cram everything. Unfortunately, this is Steve's meter, which I hate because I'm on millivolts. It's auto ranging, so it's dancing around like nobody's business. Okay, once I actually key,
it's on DC. You wanted that on DC or AC? I think it looks like it's on DC.
yeah.
Oh, well, you don't have it hooked to anything, do you?
Oh, I don't have my RF probe probing. That's why it's not reading, right? Okay, I got halfway through the
So
operation.
that's the little jumper
That's the jumper, and
the
I'm
one that we soldered on before.
right, and I'm going onto that little jumper. So it's just a way of having a nice place to hook something, a ground. I'm going to go into this hole that's right next to R at the switch. That's the output of this rig. So there's my RF probe now sitting in that.
So it's that footprint that you put on there if you happen to have a bigger switch, but it also works as a good test point too, right?
Okay.
So the one with
All
big
right.
R.
So now when I key down,
You're probing R or T?
R.
I'm at R. Okay. Remember this, that shows you which way to flip the switch, but the connection is actually the other side because it's a rocker switch. Okay.
Yeah.
So that R, if you look at the schematic, is where the output of the low pass filter comes into. So when I now key this,
Let me go back to that.
I got 3.52 volts on the meter. You can see that 3.514. It drops as you key it. Okay, so let's say call it 3.5.
Also, real quick, black or white is ground on the probe?
Black is ground, white is a signal.
Why don't you put your calculator over the white piece of paper so they can see you do the calculations?
Okay.
Oh, we can't. Yeah.
Yeah, we can.
Yep,
Okay.
okay.
So I got 3.5 volts. I got to make sure times 3.5 volts is equal to 12.25 divided by 50 ohms equals 245 milliwatts. So we read on the really nice German watt meter that we had, 265?
Somewhere around there, yeah.
Somewhere around there. And now I'm showing on my calculation with the stupid ass RF probe, 245.
The homebrew RF probe.
The homebrew RF probe is giving us 245 milliwatts. Okay. So
and that was voltage squared divided by 50 ohms.
Yeah. Okay. So now I'm going to take that out. Okay. And I'm going to go over to the junction of the first two, on the first Q1's voltage divider in front. Okay. There's the 4.7 and the 47. And I'm going to key that. And I'm reading 4.08 RF. And the schematic says it should be 3.5. So I'm reading a little bit high.
Okay.
Okay. So I know that what's happening is when I key it, This transistor turns on, the output comes through the crystal and feed back into the base, and that's how that oscillator gets working. So it shows 4 point, I'll key it again. It shows, I gotta wait for this stupid thing to auto stabilize. Come on. Jeez, more of a pain in the butt.
Yeah, it had it the first time. Now it's gone wacky.
Now I should have brought my really nice meter. I didn't bring over because it was big. Does not have auto ranging, so I set it for exactly what I want: 0 to 2 volts, 0 to 20, or what have you, and you don't get this silly crap running around. Okay, I'm gonna try it again because we were reading this earlier. It was reading okay. 4.13.
Yeah.
Okay, 4.13. And it says 3.5. So I am reading a little bit high. So I'm going to go over to the junction of the bottom of L1. Okay, here's the bottom of L1.
So that's on the output of the
on the output, and it says it's supposed to be 4.0. Okay.
Yeah, and that's the red. That's
the one in parentheses.
In red.
Yeah.
On the
okay. So I'll key down, and I got 3.66. Okay. So I'm reading a little low. All right. I can go over to the base of Q2 or the junction of R5 and R6. Well, there's the junction of those two guys. Key down, and I got 3.40. And it says I should have 3.8.
So let me bring up the schematic so people see where.
Yeah.
So the first time where you got a little high was over here.
Yeah.
Right.
Yeah.
You
see the
had,
3.5. We had four. What 4? I can't remember what it was.
4.1.
4.1.
Yeah.
I'll find out. I'll find it again. 4.1. Yes.
Yeah. And then you came
right there at the base.
Right here
yeah.
At the
so
base
here's the bottom. This. Okay. I'll key it again, and I got 3.47.
So that's a little low.
Little low. Okay.
And then you came over here, right?
Right.
At the base.
Yeah.
Of this.
I'm actually at the junction of those two at the right there.
You're
yeah.
Here.
Yeah. You see it's a straight shot between there and there. So I'll key down there, and I got 3.20.
Which is a little less.
Little low.
Yeah.
So again, you would expect it to be low if the output of the first oscillator is a little on the low side.
Yeah.
Okay.
Yeah, because this was a little low. Yeah.
Yeah. Okay. So then I can go to the collector of Q2. Okay.
Which there's right there with.
Yeah. And so and that says it's going to be 12.8.
12.8.
And I've got They don't have 12.8. I've only got 3.8.
Get an output, but
well, you got. Well, we haven't got anything on the scope. What's the output on the meter? Is it still okay?
Yeah, 0.28.
Okay.
2.6 maybe. Yeah.
Okay.
Earl says keying doesn't seem to make any difference in voltage. Maybe his straight key with mono plug is not the way to go. It could be. It's a stereo.
If it's a mono plug and is plugged in with both of those two, tip and ring soldered together, it's got the same problem that we just had.
These over here.
Yes. Okay. Because when you plug a mono plug into a stereo jack, one of those things is going to be grounded all the time.
Yeah.
The ring, the ring and the ground are going to be shorted.
So you would have to adjust this.
Yeah.
Accordingly, based on.
Yeah. So actually, if you clip the ring, clip the ring jumper, it might work.
Top one here.
Yeah. In our case, we just pulled it over here on the key.
On the schematic, that's this one. Right?
Yeah. Yeah. If you clip that one, it might solve that problem.
Yeah. And here was that first test point that you're talking about where the R is.
Yes.
So that was the first test point. And
all
then
right. I'm going to go back to that point, and I'm going to see what we got for voltage there.
This one over here, and that
we got 3.57.
Yeah, and that's what we measured the first time.
3.57 times 3.5. That's 3.57 squared. Okay, equals divided by 50 ohms equals. Yep, 254 milliwatts. Okay, so our probe is reading voltage all the way through. Now, we had a problem though. I think there's a misprint. Excuse my thing. I've never really caught before. Go back to the schematic.
Schematic.
Yeah, go back to the schematic.
Okay. Hang on a second. Schematic. Go.
See over in the output of up right there, 11.7 and 12.8. If that really was 12.8, that would mean we would have 3 watts of power going into the low pass filter. And that's not right.
Yeah.
I think that's supposed to be roughly 3.6, not 12.6. Well, 3.8, 12 point.
So you're saying that there.
I think that's wrong. Now, the schematic was done a long time ago, and apparently it has not been. It has not been.
We were getting the right output.
We're getting the right output. We're measuring the right output both with the RF probe and with the power meter.
Yeah.
And I'm saying at 12.8 RF, that can't possibly be correct.
Okay.
Okay. So we gotta fix that one.
I don't see, other than the one person who says keying doesn't seem to make any difference in voltage. Oh no, he's got the mono plug problem, so we suspect that's the problem.
Yeah. So
so
clip the ring thing and just pull the wires apart a little bit, and because I think what's happening is it's seeing key down all the time.
Yeah.
Okay.
Well, you could tell that if you had a radio nearby, you'd get what we were getting. Right?
You can hear it on the radio all the time, which is what we had.
Signal. Yeah.
Yep. Okay. So, I mean, that's how. I mean, we walked through the circuit with the RF probe, and it was spot on. No, it wasn't really spot on, but
close to spot on.
Your mileage varies depending upon the input voltage, which I never checked on this circuit right here. Let's see. I hate this meter. I hate this meter. Okay. Let me just take the RF probe clip off. Probes off the clip. And I'm still on DC voltage, and I'm going to measure my input voltage. And it should be.
So you're going between.
I got 11.85 volts.
Yeah.
Okay. So that's going to tilt something a little bit differently.
So your voltage, and that was the case on the input to the oscillator, was a little low too.
A little bit low. Okay.
So, yeah.
Now, the other thing that affects all that is the fact that, again, we've got 5% resistors on most of these things. Okay.
Yeah.
And your mileage varies because every time you put if I put this voltage divider, and this is really not 4.7K, it's 4.5K, it affects. It affects the voltage divider. Okay. So again, the reading you get is not absolute. It's just in the ballpark.
You're just trying to get it.
You're trying to get it, and we could see by walking through there, close, a little bit low, a little bit high, but we can walk that voltage all the way through, and we know what we had.
Yeah.
And the nice thing is the fact that we could put the RF probe on the output and actually calculate how much power it has, and that's expected.
Yeah.
We expected around 250, a quarter of a watt.
Yeah.
That's what the original Tuna Tin, that was all about. As a side story, the very first time I did a Tuna Tin, no, I'm sorry, not the first time. Years ago, in charge of the lab.
Charlie Armitage?
No. The lab at ARRL.
The fellow who's there now.
Yes.
Was that where they met dinner last year?
Yeah, I'm sorry. I got a senior moment. I'm sorry. I've forgotten your name. Come on. Charlie, help me.
So who is it again?
The guy who runs the lab at the ARRL.
ARRL lab director.
Yeah.
Ed Hare. Okay,
Yeah.
Finally. Okay, I fetched it out of memory bank. Ed Hare came to LobsterCon one year, and he pulled me aside and he said, I got something very precious. I got a sacred object for you. And in a box was the original Tuna Tin. The original. Okay. Doug DeMar that accidentally got thrown out of the lab and turned up at a ham fest, and he bought it and he brought it back to the lab, and he let me have it for a year.
Huh.
Okay. And I took it everywhere. I took it to Georgia. I took it to Florida. I took it to California. I mean, every ham fest, I made a trip just about everywhere. I took it to England. Okay. So that QRP guys could actually hold in their hand the original Tuna Tin too. And when I took it to 4 days in May, I was, that particular year, I was, my roommate was, oh, Jesus, I'm having another senior moment. A good friend of mine. He's an SK now. Good Lord. Help me. He was the crystal engineer at International Crystal Manufacturing. And I pulled the Tuna Tin 2 out. And I'm sorry, I'm still gazing in my memory bank trying to pull up his name. I pulled the Tuna Tin 2 out and showed it to him, and he held it, and he looked down and he says, "Oh my God," he got all excited because it had an International Crystal Manufacturing crystal in the Tuna Tin. And so he was all excited about it, and so I had to bust his balloon later on when Ed told me that he just picked up a crystal and stuck it in there because it didn't come with a crystal. He just put one there.
Okay, so the double load, the RF probe,
and the key.
we were going to look at the output on the scope so that people could see.
Yeah. Okay. All right. So we got. Let's see. We'll bring a scope into this. So I'm gonna get rid of the RF probe now.
I think it's showing up there.
And I'm gonna put the scope probe ground.
There's a little bit of lag in the scope display. So
yeah.
Apologies for that.
Yeah, we'll figure that out. Okay. And then I'll go into that final capacitor. And I'll key it down. Let's see. I got voltage still.
Yep. There we go. We got less voltage than we had
Okay.
before. Why we were only getting like 5 volts now? We were getting.
Well, that's what I expected though.
Because
Okay.
we were getting like 9 volts before.
Oh,
right?
But I think we're using the other radio.
Oh,
The other
yeah.
rig.
Okay.
Okay. So that shows a peak to peak of, looks to me like
I moved the wrong screen. Hang
looks
on.
to me like it's 0.6.
Well,
Well, that says VMRS is
RMS is
4.11.
4, yeah.
4.01.
Yeah.
Okay. So let's look at what the scope
The
says.
max is 5.7.
Okay.
So, yeah.
So the scope says that we've got 4.01 times 4.01
Zoom in a little
equals
bit.
divided by 50. 320 milliwatts.
Is that
That's
we're
what this
looking at?
says.
What did we just calculate it as before?
I thought we calculated 265. So the scope has been showing us more than the meter has.
Yeah. Consistently. It could be the probe too. I mean, the connector. Not the scope connector. But
Yeah. Okay. Well, again, now this is what we see on the screen is no longer there. He's got that on hold.
Yeah,
But
I
that
put it on
is
hold. Yeah.
that is the signal that's coming out of that. So I want to show you one other thing. Okay. I'm going to make it live again.
Yep.
I'm gonna yank the 7030 crystal out, and I'm gonna pull in and put in I happen to have right here a 3.55. We've dumped it. So I'm gonna put this back in.
So you took out that resistor R7.
No, I haven't taken out anything.
Oh, you switched the crystal.
All I did was switch the crystal.
Okay.
So I now have an 80 meter crystal in here. I haven't done anything to the circuit. I got an 80 meter crystal in. So I'm going to put the key down and let's see that scope. Okay, you got that on hold?
Whoop.
Hold that signal.
There we go.
Okay. You notice we got more voltage.
Yep.
Okay. But we've got a signal that's kind of wacko.
Yeah.
And that's because we have 80 meters and 40 meters all at the same time.
Oh, because your inductors you've put a different crystal.
No,
filter.
this is Remember, we have a low pass filter for 40 meters.
Yeah.
We got an 80 meter crystal.
Yeah. And that's
So-
what it's, yeah.
So what's coming out of it is both the 80 meter crystal and
the 40 meter
the-
that you're doing, they're filtering on.
right. Well, it's the crystal that's oscillator is actually oscillating and giving us the 80 meters and the first harmonic of 40 meters. Okay. And they combine to an ugly looking waveform.
Yeah.
So now the low pass filter that is designed normally is flat all the way till your optimum frequency, and then it drops off to take anything of the harmonic. So this is why you have to have a special filter and you're going 80 because you got to back that curve down below 40 meters, so it wipes that signal out. It cleans it up, which is why you can't change this thing without changing the harmonic filter.
Okay, some people has got some. So Earl said cutting the jumper did the trick.
Yep.
He's hearing best on 7031.
What jumper were you guys talking about there?
The tip and ring. We had both of them jumpered together. The tip and the ring
on the paddle.
Yeah. Over.
And since he had a mono plug, it was actually the mono plug will in a stereo jack will ground ring to the ground. So
he cut this jumper on the one we soldered in.
Right.
Yeah. Over.
Okay. On the board. So now he only has the tip being switching to power.
Yeah.
Oh wait, he cut the jumper on the board?
Yeah.
Yeah.
Because he was using a mono cable.
Okay. Is it the ring or the tip that he cut?
The ring.
The ring. Okay, got it.
Yeah. So when you plug a mono plug into a stereo jack, ring and ground are shorted together at the plug.
Yeah.
Because there's one big bar. The ring is not separated from ground. It's on a mono plug. It is the same. So
I got it now.
Okay. All right. So that basically freed up. So now only thing turning on his rig is the tip, which is what his mono plug was wired to.
Yeah. So let's see. We also have John says his system shows about 0.22 watts, but the RF probe seems to be measuring about 1/10 of what the schematic shows.
Really?
So if it's
1/10.
So you got the voltage squared divided by 50, right?
Right.
Depends on you've got a 50 ohm dummy load in there. So it depends on the dummy load.
Yes.
Assuming he's got the
filter is designed to have a 50 ohm. Actually, the filter is designed to not have a 50 ohm input.
Yeah.
Okay. The filter is tweaked a little bit to have more of the output impedance of that final transistor and not 50 ohms. Yeah. But the output is tweaked at 50 ohms.
And he says he's got about 2.26 volts RMS on the scope.
So 2.26?
2.26.
2.26?
What were we getting? We were getting like 4.
Yeah. Well, 2.26 times 2.26 equals divided by 50 equals 0.102. So 102 milliwatts of power, which is really low. But then again, we don't like the fact that his meter's reading very low.
Yeah.
His RF probe, I'm sorry, our probe is just out of whack. I mean, it
could be something in the RF probe then.
I think my RF probes.
Are we sure that? I mean, look at the color on the
show that on the
resistor
on the close-up camera there.
Okay.
Oh wow.
Yeah, that was really weird. Yeah. Okay, so I'm going to turn it upside down. I'm sorry. Okay, so here's the probe coming in. Okay, and that goes to this capacitor, which should be a 0.01. Why is that?
Yeah.
Okay, that should be a 0.01. Then it goes into a junction between the whoops, right there, between the cap and the diode and the.
Can you up a little bit more. Yeah, there you go, right there.
Okay, that should be.
I mean, is there a test you can run on the probe to make sure it's working?
Well, you got to have some sort of
Something to probe.
you got to have a RMS voltage to.
Right. Yeah.
Yeah, if you had a way to measure the.
Well, let me go to.
Whoops. Let's go to the overhead camera.
Yeah, go to the overhead.
Move the onto the white.
Well, I'm just holding it down for a minute. Okay, I have 4.3 megohms on that resistor. Okay, got to make sure that resistor is right. If that's 4.3 megohms, and this diode has got the bar on the. I got a wire in the way. Close up camera, please. Okay. Now, when you got that diode, and you notice that the bar is up to the top, not the other way around.
Yep.
Okay, it might be. I might suspect that
the
diode might be upside down. Take a look at your RF probe, because that would put this at roughly this voltage, which is about 0.7 of a volt.
Okay.
It would make it blind, I think.
So let's see, that first measurement you measured across the resistor, right?
Yeah, I measured it across the resistor right here with an ohm meter.
And it was 4 point something.
And it read 4.3 megohms. Okay. This should be a 0.01. Okay. And that'd be a 103 on the cap. And the diode. There's only 3 parts on the RF probe. But if that diode is at backwards, then it's going to fix this voltage point here at roughly 0.7 of a volt, I bet, or 0.5 of a volt, something like that.
He says his diode is correctly oriented. So let's see. He's showing, my system shows about 0.22 watts. Wait, 0.22 watts output?
Yeah, I think that's what he said.
So we were only getting like
0.25.
0.25. So,
I mean, 250.
Yeah. So, but the RF probe is measuring about 1/10 of that. So, yeah, there's something in there with the RF probe for the calculation. When you put the RF probe on and you measured the voltage out of the RF probe, right?
Yeah, I'm going to take the scope off.
Let's go back and do the RF
get that out of the way. And I'm going to take my meter and put it back on DC voltage. Bring my 2 leads out.
And he's got 0.226 volt RMS on the scope. Oh, you were in DC, not AC, weren't you?
I'm on DC.
Yeah, on DC. So
remember that our probe is turning RF into a DC voltage. Okay, so here's my RF probe ground. And then I'm just going to measure over at that first junction of the 4.7 and 47K. Okay, I'll key down. Well, it's kind of hard to get everybody happy in this same little. Hold on a second, don't do that yet.
Yeah, just moving it there.
Okay, I'm going to try holding that with I bent my probe now. Okay, so I'm at the junction of the 2 resistors in the front end of Q1.
Yep.
And keying down, I get 4.08 volts.
So I guess, John, the question is, what are you getting there on yours? Are you getting that same around 4 volts? Howard says, remind folks the 4 little squares that make up each section on the probe PCB are not connected. Yeah, you need to. That's where you.
That's where I showed every component was over on 2 squares, and they all overlap.
So make sure they are connected.
Yeah. Okay. Right.
Put that on the close up
there. I'm gonna do that right here on the close up. Okay. So here's the 2. Let me get my
finger out of the way.
Yeah, there we go. Okay. So here the probe comes in and I got it soldered to two things. And then the cap is soldered across. And then all these guys, that guy is this cap shorts right across that, right to the resistor.
You've got to make those connections yourself. The board doesn't have any connections.
No, which is why I ran the leads over two squares. So this capacitor runs in, is soldered. See, I'm sorry. I can't look at the screen. I got to look at the thing. So this capacitor is soldered to both of these squares. This resistor is soldered to both of these squares. And then the diode comes up and solders to the mass. So so these three squares are all soldered. These two
look
squares.
At the board. Don't bother looking at the screen.
Yeah, these two squares are soldered together several times.
Yeah.
Okay. Same as down here. I've got the diode that comes all the way over all of these squares, and then the two wires are soldered onto them.
So then Davey says he measures about 300 milliwatts with a 49.6 ohm dummy load.
Yeah.
His Tuna Helper measures 5.21 volts on the first key down, and then slides a little down as Q2 heats slightly.
Yeah.
And that's what we saw.
That's what it does.
As that heats up,
it
drops a little bit.
Yeah. Yeah.
That's not meant to be 100% duty cycle.
Correct. Okay. And that initial is what you're really going after. And as you hold it down, it's just like any other transmit circuit. When you start holding it down, the transmit section starts to heat up and the voltage starts to drop. And ordinarily you wouldn't put a dummy load on and key down for more than a couple of seconds to make a reading. So I'm not sure what we can do about the RF probe business.
Okay. So do we want to move on to other bands?
I think we'll move on, and I'll address. Send me a picture of your probe, a close-up picture of your probe in an email, and just describe what you encounter, and I'll see if I can't figure it out. And I'll send you a personal email. Okay.
Yeah. And
you got any other problem questions?
I'm looking at
Okay.
Davey KU9L.
Yeah.
I think he's just putting the equations in there for his to see how it works out.
V squared over.
Sounds like it's working correctly for him, but
V squared over R.
Yeah.
And R is 50 ohms.
Yeah, and he's accounted for the 0.3 diode drop as well. So, he measured about 300 milliwatts, and his calculation was 319. So
yeah, I mean, again, with an RF probe, and it's not that accurate.
And Howard says, might be the lighting, but his probe PCB has each section broken into 4 little squares.
He built it on the bottom side. Flip the board, flip it over.
Oh, what's the bottom side of your? Show them the bottom side of yours.
Bottom side of my board has got those 4 little squares. Each of those 4 squares are they're not the same.
Yeah.
Okay. All right. Okay.
Yeah.
Sorry about that.
He built it on the bottom.
You built it on the bottom. Yeah. Each of these 4 squares are separate.
Yeah. Okay.
Okay. But you can blob them together.
Yeah.
You just might have to blob them together.
Yeah.
Add more solder. It might work.
Yeah.
Sorry about that.
Yeah.
This is a dual function board. These are big squares and these are little squares.
Yeah.
Okay. All right. Let's rebuild that. And if you need more parts, let me know. Okay.
Yeah.
All right. Anybody else has got a problem? We'll move on to some good stuff.
Yeah. John, I think you'll catch up with John afterwards. He's seeing 1.26 volts at the junction of the 2 resistors. I assume that means R1 and R2. That's
about half of what I'm supposed to see.
Yeah.
Now the question is he sure that R1 and R2 are the same? All right. 0.7 and 47K.
Yeah.
That's important.
Are they is the right one in the right place?
That is important.
Yeah, double check to see if those get reversed.
If something reads low, you should suspect something in that neck of the woods has got an issue.
Yeah.
Okay.
Okay.
I'll take it from there. Okay. So we're going to tear this down for a second. Okay. We're going to tear it down for a second, and I'm going to do something else. Okay. I pulled my power, pull all these leads off, get this out of here. I'm going to bring in another one I built. I built this one today. Okay. let's see what do we got here. Power meters. Let's go over here. Okay, so we're gonna be doing power meter readings on this one.
Oh, you want me to get that power meter?
Yeah, we're gonna get the power.
Okay.
But don't worry about my close up. Okay, because I'll describe what I'm doing, and then you can look at the power meter. Bring me the close up one more time. Sorry about that. And I'm going to show you what I did to this.
Oh, wow.
Whoa. Okay. All right. Let me see. I got to pull this further this way. Okay. What I did was over here. This is the output transistor, the final transistor. I put a line of SIP sockets. The 3 in the middle have been cut off on the bottom. So now only this one and this one go through the board. Same as where the resistor would be. So now I can plug and unplug resistors at that final
thing what you
transistor.
did with the crystal, right?
Same as the way I did with the crystal.
Yeah.
But the crystal, I didn't cut out the underneath of, I used all 3 pins.
Yeah.
Okay. And then over here on the capacitor, on the output of the first oscillator, this is C4.
C4.
Okay.
C4, yeah.
So C4, I put a little 3-pin right there. Okay. So now I can take and change that.
And you did this just so that you can quick switch between bands. Somebody could desolder those and solder in new ones if they just wanted to permanently fix it.
I wanted to be able to show the effects of what's going on.
Yep.
Okay. So now that you know what I'm going to do, I'm going to take and I have a 2 ohm resistor right here. Red, black, gold.
So you replaced
I took 56 ohms out and put 2 in.
Yep.
Okay. So now I'm going to measure I'm going to look at the output of the power meter.
Okay.
And everything. Let me power on. And you better change the scale.
Yep.
We're going to change the scale to the 1 watt scale. Okay. I'm going to key down. Boom.
So now we're up
at 700 milliwatts.
Yep.
Okay. That's a respectable signal.
Yeah.
Okay. Now I'm going to pull that 2 ohms out and I'm going to put in a very dangerous 0 ohms.
So if we're looking on the schematic,
I'm changing.
we're over here at R7.
R7.
Right.
I'm changing
So-
R7 now to 0 ohms. So now I have nothing in that circuit.
So we went down to 2 ohms and now, so you're dropping from 56, but
Okay.
okay.
So if we look at the power meter, I put an output, boom,
Now almost 0.8.
almost 750 milliwatts.
Yeah.
Okay. So as you can see, by changing R7, you can increase the power. Now, of course, watch what happens though.
Oop.
Back to the meter. I'm going to go up.
Then it drifts.
See
down.
how that drifts
Yeah.
faster? Because now that transistor is heating up fast because there's no resistance in that output. In fact, it's warm.
Yeah.
And you should only use a low resistor if you've got a heat sink on the transistor. Okay. Now it's pretty hard if you try to find a heat sink for a TO92 thing. They're going to cost you an arm and a leg. But if you happen to have an old metal cased 2222, which are unobtainium these days, okay, which is why I don't put one. In the early days, I would put a metal cased TO18 and then a TO92.
Yeah.
So that this thing here, you can put a heat sink on and you could crank it at 0 ohms.
And we put that thing in a socket so that when you do this experiment.
Yeah. See, that's the other thing.
Blow it up.
I forgot to say, I also socketed the 3 pins for that transistor.
Yeah.
Okay.
So that, I'm going to need to turn this on.
All right.
But
so
you put those in a socket.
See, I put three socket pins. Okay. And so I forgot to mention that. So that is socketed, the resistor socketed, and that capacitor socketed. Okay. So the idea is, in fact, you want more power, you have to drive that output transistor harder.
Yeah.
And if you drive it harder, you might blow it up. Okay. Well, in the case of a TO92 transistor, I mean, you pull that.
Pretty cheap to get another
one.
Well,
Look, I pull that out and I can put another one in. Okay. In a matter of seconds. and it doesn't cost you much. Now you could buy a 3866 or a bigger transistor, 2222, that's in a can, or a 2219 in a can, and you put that in there with a heat sink, and now you can drive it with 2 ohms all day long. You're still not going to power on for eternity. You're still going to drive it at some speed, some sending speed, in which most of the time it's off.
Yeah.
It's not on. So not a big deal. Okay. So the idea is the fact that, you can take and boost up the power. And sometimes what I've done in some versions of my Tuna Tin, I've actually put a pot there, a small pot.
And you can dial it up and down.
Dial it up, dial it down. I think there's a pot on
there. You can break through the pile up with 700 milliwatts.
Yeah, that's correct. Okay. Because it does take about a half watt. If you want to run into a tuna topper or a Texas topper, it takes about half a watt of input power to get 5 watts out.
Yeah.
Okay.
Yeah.
So you need to break over that half a watt barrier. Now, again, I can take that crystal out and put in my that was my 80 meter crystal. Okay, so I put that 80 meter crystal in there.
So where would you be?
Okay, so let's pull up something else. That was the one thing I wanted to show you, that you could change the final resistor R7, lower it, and get more power. Okay, now pull up that TTT schematic 8.
Oh, the other.
The other schematic.
The other schematic.
When I first started kitting Tuna Tin 2s, and I had, see on the bottom right, it shows a TO18 with a round can.
Right. Yeah.
Okay. So by putting that in the kit and putting a heat sink to it, you could get more power out.
Yeah.
Look at where's R7 on this schematic. I can't read it because it's too far away from my glasses. R7 looks to be a potentiometer.
C13.
See, right in the very middle of the board.
In the very middle of the
right
board.
there, you just went over it right there. R7. Isn't that R7? Doesn't that show a pot? 100 ohm pot.
Yeah, that's what.
And what's above it? A 5.6 or 6.8 or 6.8?
6.8.
6.8. So I showed in the original Tuna Tin I was kidding years ago, that's got a 100 ohm pot that you can crank down to 0 or any other value. Okay. But it's got a minimum of 6. If you crank that pot to 0, there's still a minimum of 6.8 ohms in that thing. And I found that to be acceptable for not blowing up the final transistor. If you happen to key down for a minute or something, it wouldn't get hot enough to burn up.
Yeah.
So that's another way of doing it. Now down below there's a table, because right there showing the C2, C6, 7, 9, 11, L2, and L3. Yep. C2 happens to be, let's go back up in the circuit, it's the output of the first oscillator. Back up a little bit, no, other way. Okay, see that C2 right there? That's the output of the oscillator. And at 40 meters, it's 100 picofarads. Okay. Now, if you want to go to 80 meters, that on the table, it says you should put a 220 picofarad there. So by putting on my board, by putting a 3-pin socket underneath that C2, I can pull it out and change it. And I'm going to find my 220 over here, which says recommended for an 80 meter. So I'm going to put a 220 there, and I've got an 80 meter crystal in the socket.
Where are we going to end up?
Huh? We're going to end up on the, put it on the 5 watt scale.
Oh, I figured we were going to pick you up on the radio.
You could. It would be at 3.55, I think. I mean, look at that crystal. So you want to go to 3, no, I'm sorry, wrong crystal. You want to go to, that's the wrong crystal. There's the right crystal. Nope, that's the wrong crystal.
We're all the wrong crystal.
I've lost the crystal. Oh, Where's the other one? Oh, here it is. I still have it in the old the old board we were playing around. 355. So you want to go to 3.54 maybe.
3.554. No, that.
Yeah. You want about 1,000 hertz below or above the marked frequency.
So 3.554.
No,
Okay.
no, 354.
Just 3.54.
No, 355. Yeah, 354. Yeah,
3.540.
Yeah. Okay, we got to put a dummy. We got a dummy load in there. Power's on. You looking at that meter? I can't see it.
Okay. Oh, that's my finger.
You got the 5 watt scale.
5 watt.
Oh yeah. 5 watt scale. That's 1 1/3 watts. Okay. Now, because we have a 40 meter low pass filter in here, which is okay because it's going to pass 80 meter signals through there.
Yeah.
But it's also passing
the 40 meter.
The 40 meter harmonic, which is bad.
Yeah.
Okay. But I'm showing you that by changing the crystal and changing that C2, you can make this thing easily go to another band, but you have to change the filter. Okay. And
to make it operate.
To make it legal.
Yeah.
To make it legal.
Make it legal. Yeah.
Yeah. FCC frowns on you putting out, because if you got an 80 meter crystal in there and you're broadcasting on 355,
yeah,
you're also broadcasting on 711.
Yeah.
712 or something of that nature. Okay. So you're on the second harmonic. Okay. Because that's not shorted the ground, the harmonic.
Yeah.
Okay. Well, I'm sorry. So what I ended up with is I had 4 different kits I sold. I sold an 80 meter, a 40 meter, and a 30 meter, and a 20 meter. And I had them all, and I was putting all the parts in the cans. Okay. So I had them on the shelf. And quite often I would always have orders for 40 meter. And if I put a bunch of 80 meters up there, they'd be there forever. But some people like that. Well, now 20 meters is pretty, it's a very active channel band.
Yeah.
So I sell a lot of 20 meter stuff, but you could easily port this harmonic filter to 20 meters, put a 20 meter crystal in there, and away you go.
Yeah.
By changing C2 and the harmonic filter, and you can vary the power by R7, you could get a respectable signal on 20 meters with a Tuna Tin.
I haven't seen any comments or questions.
So on going back to TT, the Tuna Tin schematic for a TTT schematic.
The 40th anniversary schematic.
No, the TTT schematic 8.
And that would be this one.
Okay, so right there at that table,
yep.
there's the capacitor values and the inductor values. Now, and this is going back a ways. Those inductors are toroids, wound toroids, because we built that circuit.
So like the 80 meter here.
Yeah. Okay. So in this case, the components for the capacitors are standard values,
yeah.
But that involves having to have weird inductances to make the filter work. So you had to wind them.
Yeah.
Okay. And that's the thing. People just didn't like winding those toroids.
Yeah.
So
all that's right up here, right? This is the.
Yeah. Well, there's 40 meters. So you can go into a calculator program and see what 23 turns on a T2 transistor. You can see what that supposedly comes out on.
Yeah.
Okay. But see the date, 2006. Okay. I was, kidding Tuna Tins way back then. I mean, that's a long time ago, but even before that, because I started off with just 40 and then I started gradually going to other bands.
Yeah.
So the fact is, I mean, the Tuna Tin 2, you can make it on any of the bands. the oscillator circuit and the final circuit are pretty frequency friendly.
Yeah.
Up to
They're
about
moving
10,
around. Yeah.
up to 10 meters.
Yeah.
Okay. So that's what's
So,
kind of nice about
If
this.
people got questions, post
Yeah,
it in there.
this is it. We've
We've-
covered everything we could cover.
We've gone to the end of the pre-programmed material.
That's right. I mean, I think we've got everything, all the bases are covered. The fact that you can go kind of crazy and you can put it on other bands, you can increase the power, you can make it. And that's why, that's why I went to and created the Super Tuna.
Yeah.
Because it has plug-in band modules, and now you can change the band from 80 to 20 in 10 seconds.
Yeah.
And away you go. And you got more power.
And you've got the filter and everything.
And
right
you
on
got
it.
an RF probe built in.
Yeah.
And you got a dummy load built in. So all that stuff was all built in for a little more money. So the Super Tuna was the way to go. And so I standardized on the Super Tuna, and the Sudden Storm, which is the receiver matching. It has a band module also, so that you can change the band module. If you had two tuna cans, a Super Tuna and a Sudden Storm, and a collection of band modules, you can just change that for 80, 40, 30, 20, and 10.
Yeah.
In a matter of seconds. So I think that's all I really wanted to cover. I mean, if you still have problems with your Tuna Tin, send me an email direct, and I'll figure out what your best approach to figuring out what your problem is.
Yeah.
I would check your RF probe a little bit. Obviously, we got one built on the back side that you might have a little soldering issue there. But I mean, it does work. It's pretty simple.
Charlie, did you get yours up and going? Did it work?
No, there's still some problems. I'll meet with Rick sometime.
Oh, come on. Okay.
I don't need. I've been. It might be something else.
We've only been on the air for an hour and 27 minutes. Okay.
I know, but I keep testing a whole bunch of different stuff, and I'm like getting back. I mean,
Okay.
I don't know at this point if it's my meter, my power supply, the RF probe, the radio, the keyer, or all of the above. Because I've tested each of them, and I'm not getting results on any of them.
What you've got to do is you got to throw certain things out of the equation first.
That's what I am. That's what I'm saying. Is I tested them independently. Even the keyer, I'm like, anyway. We'll talk.
Okay. I'll be happy to resolve those issues. I mean, it shouldn't be that hard to get it to work. I mean, that's the whole idea about the Tuna Tin, was it's so simple, the circuits.
Yeah.
I mean, I've only got one rig that's even simpler, and that's the WBB.
Yeah.
It's only got one transistor.
But yeah, when your test equipment isn't working the way you expect it to, then it's like,
then you gotta sit down and say, okay, let's figure out what's going on.
Yeah, I think actually it might be my power supply and my DMM, because my power supply should be reading 13 right out of the probes of the power supply. It's not power supply, just a battery.
Yeah.
It's
No. It's not just a battery, because a battery could be
it's
a
a life
terminal
pole.
voltage on a battery from anywhere from 10 to 14.
It's a
depending on how
life
fresh
pole
it is.
that's supposed to be 13.6 and it's 10.
Yeah.
Well, that's because it's not fresh. It's not fresh off the charger.
No, it is though. That's the thing. It's fresh off the charger.
If it's 10, it's dead.
Yeah. Well, so there's that. Then there's the whole thing that I took when I pulled the DMM out of my case here. It was on, and the screen was blank. So I'm like, oh, that's not good. I'm gonna have to switch the batteries.
9-volt battery inside there.
But I turned it off and then back on, and it fired up, and so I just left it. But I think maybe there's something wrong. Anyway,
okay.
I have some stuff I got to figure out before we get
All
there.
right.
And
Well,
Earl says he's listening on shortwave radio. He hears background noise, and when he keys, the noise lessens, but he doesn't really hear a good tone.
he's got to go off frequency. He's hearing this squelch. His radio is squelching because it's dead zero beating on the rig.
So you don't want to be on 703.
Well, no, hold on a second. Okay, one thing. A 7030 crystal doesn't always oscillate at 7030 because it depends on the oscillator circuit you put it in, how much capacitance is on that crystal. So a typical Tuna Tin 2 circuit might, if you put a 7030, it might be 7035.
Yeah.
Okay. It might be, it might be anywhere from 0 to 1K off. Okay. Now, once you find out where it is, Then you got to go about 700 hertz either side of that to be able to get a beat frequency on your receiver.
Yeah.
Because if you tune directly onto what you've got for a crystal,
Yeah.
you're going to be zero beating, and you're all you're going to have is squelch clunks.
Yeah.
Boom.
Yeah.
Boom. Boom. Okay.
Yeah.
If you move that off by 600, 700 hertz, you're going to have a tone.
Yeah. So just move it off.
Move it off.
And you should be hearing.
The further you move, the higher the tone.
Yeah.
Okay.
Davey says he's looking forward to upping his power to 700 milliwatts.
Well, Davey better get himself a good heat sink on whatever he puts in there.
He also wants to get it on 10.116 for Parks on the Air. So
yeah, that's pretty easy to do. You got the data right there.
Yeah.
If you look at another thing to mention is if you look at the schematic for the Tuna Tin 2 40th anniversary, you'll notice that it's a 2 pi section low pass filter with every component on the board. In other words, there's 3 capacitors for the 2 sections. There's 2 chokes. Okay. And then there's 2 capacitors paralleling those chokes. So you can look up in practically any of the low pass filter tables and find a low pass filter configuration that will fit that.
Yep.
Because everything is there. Okay. Yeah. Sometimes you don't need the capacitors paralleling the choke, but for the point is they're all there. So you can go like Ed Weatherhold published a set of values that everybody in the QRP frequency community uses. Yeah. Ed Weatherhold, I can't remember his thing, but they showed up in ARRL and they're in.
Just go look them up.
Look them up.
And
okay. And all you got to do is just put those values in that filter, change C2 in the crystal, and you're someplace else. 10.116. Yep.
Okay. I haven't seen any more things coming in.
Okay.
I have one final question. I want to put Rex on the spot.
Uh-oh.
He's not prepared for this question.
Okay.
What's next?
What I can't let the cat out of the bag for a certain thing.
Okay, that's a great answer.
You've almost made him speechless.
I have something I've been working on that when I get it done. Now I put a lot of energy into this. I mean, this has taken 2 months to kit them, to make all the documentation, and to go through all this harangue on the Tuna Tin. Something that I've been eating and breathing and sleeping for 20 years almost. So I haven't had a lot of free time. Plus the fact that I fell off a ladder twice. Okay. Ripped open my leg, come down with COVID, broke my elbow, all this stuff in the last month and a half. So, I mean, I'm a hurting cowboy. I haven't done too much extra stuff.
Well, would it be safe to say that this isn't the last that we're going to do this teamed up?
Oh, no. I don't think I can do one for February, and I don't. I'm thinking maybe end of March, maybe another live stream with a kit. I'm thinking about doing some quickies where there is no kit. I just go online and we show something that's of interest to anybody who's doing QRP rigs. Playing, doing some sort of a trick or something of that nature that is just fun.
Maybe even just sending out an email or a post saying, "Hey, gather these parts, have them ready, and then we're going to make something."
Well, hey, next weekend is the big giant Ham Fest in Orlando, which I would love to be there, but I don't have enough money to go. I used to go to that one every year because my father lived 45 minutes away, so I could always make a trip to my father, and he always bought me a ticket for the Orlando Hamtation. But
I think I just wanted to kind of draw out of you that we've been talking, and I think that this is not the last time we'll be doing this series like this.
I was hoping I could do 3 or 4 of them this year with an interesting kit. I've got a couple of things brainstorming in my. I don't want to. This one I did because the Tuna Tin is so ubiquitous as being classic QRP, and I had it, and I've got all those values burnt in my brain, and it was pretty easy to do something. But I'll do something different, something new, and I'll probably schedule it for the end of March.
We're not going to tear down the studio just yet.
No, we're not going to tear it down and set. As long as Steve continues to be my right-hand man here in the behind the console, we're good. I like doing this stuff. I mean, I can't go to every Hamfest anymore. I'm getting up there, and my Social Security money doesn't cover travel to all these different Hamfests. I used to go down to Albuquerque all the time because I had a really good friend who actually put that one on. I didn't get free transportation, but I did get a free place to stay. That was nice. And so I went there like 3 or 4 years and did Buildathons. But yeah, I'd like to do something. I did the first time I did a live stream myself. I was doing it late Sunday night, and I just had a gantry camera over my thing, and I started playing around with unsoldering stuff. And all of a sudden, I gathered a crowd of like 12 people. I thought it was pretty funny. So I might try to do that as soon as I can find a place to permanently set up just a one-man, stupid thing. So these, sorry, Steve,
no.
These, really big live streams. I mean, we got, how many cameras we got? 1, 2, 3. We got 3 cameras, microphones, switching into, switching in oscilloscopes and schematic and everything else. One guy can't pull that off.
Well, you're broadcasting to 3 different platforms too.
Yeah, and we're
2 different YouTube channels and Facebook.
Yeah, that's not a one-person job. But I could sit at my bench and just blah 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 on something.
So Joseph asked, what kind of antenna would you plug into this thing?
Well, obviously it's 50 ohm output. So you got to either go into a tuner if you don't have anything that's 50 ohms.
Yeah.
Okay. Let's face it, you're at a disadvantage by not having almost a whole watt of power. So you want something as efficient as you possibly can. A lot of people use end-fed half wave.
Yeah.
But I mean, we've done Buildathons in the past for the QSO Today Buildathons where we included antennas and simple wire antennas. Most QRP guys really like super easy to hang wire antennas. I would certainly go with that. A vertical of some sort.
For me, I'd go with a single band, a mono band dipole. It's easy, most efficient.
Yeah, if you got 2 places to put the dipole up on.
Yeah.
But I mean, obviously that's going to give you your best radiation, your best signal. But you have to point it somewhere, because you're only going to be working broadside, left, backwards and forwards. So you're only not going to talk to somebody. With a vertical, at least you can talk to a whole bunch of people. I got a stupid vertical in my side yard where the dog is, but I've never used it. I haven't used it in a long time.
Yeah.
So, but I'm going to try to actually set up. Quite frankly, I have no space. I can't load a space, but I don't have it because it's full of stuff. So I am trying desperately to get someplace to set up.
And I'm sure you'll put on your channel and send out your letter.
I certainly all the people who sung on this, I got a nice email list of you. I think there's like 60 or so people. I mean, it wasn't a big number, but I'll do a list. But Charlie's interested in continuing to broadcast more, and Steve's really with me. So we'll do it again.
I'd love to. March. I like just building along with you too on the side and coming up with questions as I go. Yeah. Except for this one, I got too many questions. So I'm like, I guess I better just wait.
You can get me you got my number, so you can hit me sometime when you've got plenty of time. And I really don't do anything else. I mean, I'm QRP pretty much all day long. I do have a couple other things I have to do. Usually it's on a honeydew list, but I do have to do them sometimes. So anyway. Okay. I want to thank everybody for participating, and I know this was very intense that we did 3 sessions on one kit, but there was a lot of information about taking this further. That's what I wanted to show. It's the fact that you can start out with a simple kit, but you can take it.
Yeah, you can do more.
You can do more. Yeah. And you can do more for $30. You can do lots more. You just got to know you have the right information, take it further. And I think we've got it all for you now. And most of it, I look through all the files on the website because I think I've covered most everything about what's going on. So, and of course, now we got 3 nice videos you can watch at your leisure. Repeat. Oh, ikuté with day. Okay, I thank everybody for participating, and we'll do it again.
Okay, guys. Yep. Catch you later. Talk to all you guys again.
Bye.
See ya. Thanks, Charlie.
Thank